Okay, so this is our second of two videos on the cross product for Math 1410 linear algebra. In the previous video we went over the definition and a number of ways for remembering the definition, which admittedly is a little bit complicated looking at first. And so we saw that there's this sort of, determinant trick for remembering the cross product. There's a few ways of trying to remember it, and it really doesn't matter which one you work with as long as you find one method that works for making sure that you get the right outcome. So this time we want to look at some of the properties that are satisfied by the cross product and understand why we actually care about this cross product, why it's useful. So this first property, we mentioned this last time, and it is the most important property to a large extent. So the fact that the cross product is always orthogonal to both vectors u and v. Now, there are a number of situations as listed here and here. There are situations where the cross product could come out to be 0, right? If either u or v is the 0 vector, or if u and v are parallel, then the cross product comes out to be 0. And these are sort of degenerate cases. The interesting case is when u and v are non-zero, non-parallel vectors. And even in that setting, when you compute the cross product, you can verify that the cross product is orthogonal to both u and v. And so what does that mean? That means that if I take the dot product of u with u cross v, that should give me 0. If I take the dot product of v with u cross v, that should give me 0, right? So the cross product is orthogonal to both u and v, and this is one of the things that makes it especially useful. Some people will tell you that you can use the cross product as a test to see if two vectors are parallel, but this is a useless test, because remember that what it means for u and v to be parallel. V is parallel to u, right? This means that v is a scalar multiple of u. And it's really easy to see if two vectors are scalar multiples. You just check to see if each component of v is the same multiple, the same common multiple of the corresponding component for u. This is easy to check. Computing a cross product takes a fair amount of work, so it's not something that you would want to use as a method for determining if vectors are parallel. Okay. One of the other properties which can come in handy, especially if you're using cross products in some of the contexts in which they are used in physics and other applications, is that the cross product is anti-symmetric or anti-commutative. If you change the order of the two vectors, you get a minus sign. So u cross v is the negative of v cross u. So swapping those two vectors gives you a minus sign. Another of the properties you see here is that placement of scalars is sort of irrelevant. You can either multiply u by a scalar, you can multiply v by a scalar, or you could multiply the whole cross product by a scalar. These all come out to be the same thing. And finally, the cross product is distributive, which is useful. One interesting thing about the cross product, however, is that the cross product is not associative. So the vector, so let's just add this as a note. So if you take u cross v, if you take the cross product of two vectors in R3, this is once again a vector in R3, so you could then take the cross product of that with a third vector, let's say w. That turns out to not be the same thing as doing u crossed with v cross w. So it's an interesting thing. This is one example of sort of an algebraic operation where placement of brackets really does matter. And so you rarely see any sort of discussion of extending the cross product to cross products of 3 or more vectors, because then you have to worry about how you group them together. You get different answers depending on how you place brackets. Now, one other thing you can do with the cross product is this scalar triple product here at the bottom of the screen. If you take the cross product of v with w, and then you dot it with a third vector u, you get this expression here, u1, u2, u3. So this is an example of a 3×3 determinant. And so at this point, if you want to, you could think of this as just a way of telling you how a 3 by 3 determinant is computed. But the idea here is if you kind of expand along the first row the way we did when we were computing cross products in the last video, you want to think of this as u1 times the vector, sorry, the number v2, v3, w2, w3, right? So the same sort of story as before, that you know, for the u1 you delete the row and the column containing u1 and you take this 2 by 2 determinant of what is left over, and then minus, remember that minus sign right there, times, so if I delete the middle row or the middle column in the first row, then what's left over is v1, v3, w1 here. Oops. w1, w3, and then u3 times v1, v2, w1, w2. So you can expand like that. So we'll come back to that later on. Okay. So let's see that this actually works, right? So I've made this claim a couple of times now that the cross product is orthogonal to both of the vectors, right? So this is a theorem. Okay, so for any vectors u and v in 3 dimensions, if I do u dotted with v cross w, the result is going to be 0. Okay. Oh my, sorry. Not v cross w. Getting ahead of ourselves. That's certainly not true. What's w? No, w is u. U cross v. There we go. So u is, orthogonal to the cross product involving u. And similarly, of course, you could also say that v is orthogonal to this cross product as well. We will just prove one of them because the argument for the other one is basically identical. So how do you prove this? Well, we wanted to make this general. So we choose component representations for our vectors, but we don't say what those components are. So u is going to be u1, u2, u3. V is going to be v1, v2, v3. And so we calculate the cross product. So we know that the cross product u cross v, right? So this, if we work it out using this 3 by 3 trick, so we write u1, u2, u3, v1, v2, v3. Okay, so if we expand everything out, this is going to be u2, v3 minus u3, v2 times I minus u1, v3 minus u3, v1, j plus u1, v2 minus u2, v1, k. So how do we do the dot product? Well, if we want to dot this with u, then we've got to take this guy and multiply by u1. We've got to take this guy and multiply by u2. This guy multiply by u3. So the dot product looks like u dot u cross v. It's u1 times u2 v3 minus u3 v2 plus, well, actually let's put it in as a minus sign, right? Keeping track of, so this minus sign is coming from this minus sign up here. So u2 times u1 v3 minus u3 v1 plus u3 times u1 v2 minus u2 v1. So Expand everything using the distributive property. What do we get? U1, U2, V3 minus U1, U3, V2 minus U2, U1, V3 plus U2, U3, V1 plus U3, U1, V2 minus U3, U2, V1. Okay, bit of a mouthful, but now let's have a look. U1, U2, V3 shows up here, and down here notice I've got minus, well, U2, U1, V3, but these are numbers, order of multiplication doesn't matter. Alright, so those cancel. Okay, minus U1, U3, V2 is sitting here, but over here I've got a plus U3, U1, V2, and again switching those U's, those are the same thing, right? So I can cancel those. And finally, U2, U3, V1 minus U3, U2, V1. Again, those two are opposites of each other, so those cancel. And everything cancels out. I'm just left with 0. Okay? So dot product comes out to be 0, and I haven't said anything about what the vectors are, so we know that this is going to be something that's true in general. And you can check that if you replace the U1, U2, U3, if you replace those with V1, V2, V3 for the dot product with V, you still get 0. The outcome is the same. Okay, now this next result, it's not something that I'm going to try to prove. You can do it, but I'm not going to. So this Lagrange identity, it gives you a way of relating the cross product and the dot product. So it tells you that the magnitude of the cross product, so the magnitude squared, right here, okay, is equal to the magnitude of u squared times the magnitude of v squared, and then you subtract off the square of the dot product. Now, establishing this identity, if you want to give it a try, feel free to give it a try as an exercise. It is an exercise in sort of algebraic stamina, right? Because remember that what you're doing here on the left, the magnitude squared means you're taking the dot product of a vector with itself, u cross v cross u cross, or dotted with u cross v. That's the left-hand side. And now think about how complicated here's the cross product. It looks like this. And so you're going to, you'd be doing this guy squared plus this guy squared plus this guy squared. You have to square out all three of those things, add them up, simplify, and check to see that you get the right-hand side. It's a fair amount of work, so it's certainly not something that I'm going to be able to fit on the third of a slide that I have available to me here. But what I can show you is that this does gives you a nice formula for the magnitude of the cross product, because you might recall that one of the formulas we established for the dot product is that u dot v is equal to the magnitude of u times the magnitude of v times cos theta. So that tells me that if I do, so assuming that this Lagrange identity holds, it does. I guess you have to take my word for it. So I get magnitude of u squared, magnitude of v squared, minus, so if I square the dot product, what do I get? I get magnitude u squared, magnitude v squared, and I get cos squared theta. So take out the common factor. I've got 1 minus cos squared theta. And what is 1 minus cos squared theta? That is sine squared theta. So I get length of u squared, length of v squared, times sine squared theta. And so this formula here for the magnitude of the cross product, this follows by simply taking the square root of both sides of that equation. Now you might be concerned about positive or negative roots, but of course magnitudes should be positive by construction, right? You can't get a negative magnitude. Why is sine theta? Why do I know that should come out positive? Well, the way we generally define the angle between vectors, we define our angle to be somewhere between 0 and pi, between 0 and 180 degrees, and sine theta is positive over that whole span, and so we don't really have to worry about the sine issue there. Okay, so here's an example. How can we find the area of a triangle given these three vertices? Well, let's come back to this formula here. Okay, magnitude of the cross product, magnitude of u, magnitude of v times sine theta. Let's keep that in mind, and let's draw ourselves a picture. So I'm going to draw a picture, and again, remember that pictures don't have to be accurate. I don't have to necessarily plot these points according to the coordinates that are given. I just need to draw a picture that has 3 points in it. So let me draw those three points, P, Q, R. And let me construct two vectors, V, W. So what are V and W? Well, V is the vector from P to R. And remember, the way you construct these direction vectors is you take the coordinates of the head, you subtract the coordinates of the tail. So for the vector from P to R, 1 minus 2 gives me minus 1, 0 minus 1 gives me minus 1, 1 minus 0 gives me a 1, W, PQ. Okay, so I do the coordinates for Q minus the coordinates for P, so 3 minus 2 gives me 1, minus 1, subtract 1, minus 2, 1 minus 0 gives me 1. Okay, now, where is the triangle I want? So the triangle I want is here. Let's close this off, okay? Here's the area I'm trying to find. Okay, now, one of the kind of tricks you can do here is you can complete this thing to a parallelogram. Okay, so we complete this thing to a parallelogram, so the area of the two halves is the same, right? So let's call PQR our S. Let's mark that last point, and I guess we should, let's keep our colors consistent, right? And so one of the things you can see is that the area of this triangle PQR, that's 1/2 the area of this parallelogram PQRS. That much is clear. What is the area of the parallelogram? You may recall a formula from high school, you may not. Let's put in this theta. So the area of a parallelogram is equal to, so this area is equal to, so let's actually go over here. So the area of this parallelogram, PQRS, it's equal to the base times the height, where the height is here, okay? Here's the height. Okay. The height is measured vertically, right, at a right angle here. Okay. So the length of the base, well, that much is clear. The length of the base is V. What is the height? Well, if I look at this right-angled triangle here, the length of the hypotenuse is the length of W. The height is opposite that angle theta, and so the height is given by the length of W times sine theta. And we just argue that that's equal to the length of the cross product. Okay, so now we know how to find the area of our triangle. The area of our triangle is going to be half the magnitude of the cross product. So we better start by finding the cross product. So V cross W, I, J, K, minus 1, minus 1, 1, 1, minus 2, 1. Okay, I get I times minus 1, 1, minus 2, 1, minus J, times minus 1, 1, 1, 1, plus k times minus 1, minus 1, 1, minus 2. And let's work these out. So minus 1 times 1, that's 1, minus 1, and then I'm subtracting minus 2. So minus 1 subtract minus 2 is minus 1 plus 2. Comes out to a 1. Here I'm doing minus 1 minus 1, right? Minus 1 times 1 gives me a 1, right? Remember how we do this. We go this way. That comes out to be a minus 1. That comes out to be a 1. And I do this guy minus that guy, so minus 1 gives me a minus 2. But I got this minus sign out front, don't forget that guy, so minus 2 gives me a plus 2. Minus 1 times minus 2 gives me 2. I'm subtracting minus 1, 2 subtracted from, or minus 1 subtracted from 2 is 2 plus 1, so I get 3. So 1, 2, 3 for my cross product. Feel free to check that if you take the dot product of either v or w with that cross product, you do indeed get 0. And so now we know what the area should be. So the area should be, so the area of this triangle PQR should be 1/2 the magnitude of v cross w. So that's 1/2 the square root of 1 squared plus 2 squared plus 3 squared, so that's the square root of 14 over 2. Okay, moving right along. You can also use the cross product to compute volumes. I'm not going to kind of go too much into the details here, but if you go through carefully, if you play around, and if you believe this rule I've given you here, which is that for the volume of a solid, in fact this is something that's true for any solid with kind of a constant cross-sectional area, the volume is given by the area of the base times the height of the object. And so the area of the base, well, based on what we just argued, we know that now the base is a parallelogram, right? Here's our base, right? It's a parallelogram spanned by the vectors v and w, and we just saw that the area of any such parallelogram is given by the cross product of the vectors defining to the adjacent sides, and the height, so there's our angle theta, right, between u and the cross product. And so again, kind of playing around with trig, we can work out that the height is simply given by the magnitude of u. Here's the vector u times cosine of the angle. That will give me the height. And so if you put these things together, what you get is that the volume is, so it's the magnitude of u times the magnitude of v cross w times the cosine of the angle between those two vectors. But that's simply the dot product. And so this scalar triple product, sometimes called the box product that we referred to on the first slide, shows up here. So this scalar triple product, taking the dot product of one vector with the cross product of two others, gives you the volume of this three-dimensional parallelepiped, as it's called, that is formed from those three vectors.